Here's a little warm-up activity. Go ahead and do these problems right here. You also want to make sure to pause the video so you can try them before I show you how to do them. Now that I've given my warnings, I'm going to go ahead and start doing these problems. For the first one, we first want to find the derivative before worrying about what this number is used for. So let's do a derivative using the power rule. So when you do the derivative, you're going to end up with 0 minus 3, so negative 3. And we don't even have to plug in the 2 to find out what that slope would be. So the slope is the same everywhere, negative 3. For number 2, power rule again. However, when you do the derivative, this time we still have an x, so we have to plug in for the x. Plug in this negative 1, you're going to end up getting negative 2. So the slope is negative 2 at the point negative 1, negative 6. This one's going to be a little bit trickier. We have to multiply by the bottom conjugate, which is not what we used to. We usually, in the past, I've shown you examples where we will multiply by the top conjugate. My hope is that after multiplying, this entire bottom will end up being x minus 9, so I can cancel this out. Because as it is right now, I can't simply put in 9 in here since it's going to cause a 0 in the denominator. So let's see what happens. So we do have an x minus 9 on top and bottom. They do cancel. So you have a square root of x plus 3. You plug in a 9. You're going to end up getting 3 plus 3, which is 6. Blah. Alrighty, for the last one, we want to factor this, because if you plug in 2 right now, you're going to end up getting a 0 in the denominator. So when you factor it, it's going to be x minus 2, whoops, my pen's not writing, x minus 2 over x minus 2, x plus 2, that's factored, the x minus 2's cancel, so 1 over x plus 2, and when you plug in that limit, because now plugging it in is fine. Okay, pretend I write x approaching 2. We're going to end up getting 1 over 4. That's how I do now. Let's move on. Today's objective, students will determine the intervals of increase and decrease of f of x and sketch the graph of the derivative of a given function. Please get this in your notes. So, find the derivative has always been easy. In this case, x squared plus 5, when we want to find the derivative, we just use the power rule, it's 2x. So a parabola will have a linear derivative. When we want to find intervals where it increases and decreases, it's very important that we find the zeros. Because when a derivative is negative, that means that the function is decreasing. The change of rate of the function when it's negative should be decreasing. So we could still be in the positive, above the x-axis, the positive y range, but it's going down. So for instance, this right here is an example of a function increasing while still be in the positive first quadrant, the positive y range. But then you could have a function like this. You still have positive values, but it's decreasing. It's lowering in y value. These are negative slopes. Yep, we want to find all of those bad boys. You have this in your notes. Find the zeros of the derivative, which ends up being the maximums, minimums, and plateaus. Please get this in your notes as well. We are very interested in the zeros on the derivative because what they represent are maximums, minimums, and plateaus. Plateaus just mean that it's not maximum or minimum. It looks something like this, where wherever it's kind of, you notice how there's a flat area. I'm not really good at drawing. That would be the plateau. That would be an example of having a derivative being 0. Now you also want to do these. Find the intervals of increase and decrease, then draw the function to a derivative of f of x. Alrighty, so this is a parabola. which we can see below. And the best way to draw it in this case, they just factored it, got the little x intercepts, and then they found out what the vertex is. The vertex ended up being right there. And then you can draw the parabola really easily that way. And then for the derivative, it's a line, so you draw the line. Now, what's the interval of increase and decrease? Well, we noticed that the derivative hit 0 at 1, which also happens to be the parabola, the parabola's vertex. And the vertex, as you know, is the place where something changes. So for instance, you notice how this arrow right here looks like it's pointing this way? It's not really the case. Really, the function is coming from the left side and it's going down here. But at that point, it's changed direction and now it's increasing. So at 1, that's where the change happened. So the interval of decreasing would be from negative infinity, don't include a negative infinity, you cannot include that in the set, all the way to 1, and we also don't include that point either, because at 1 you cannot make an argument that it's increasing or decreasing. And then it's from 1 to infinity. That right here will be the interval for the increase. So the decrease will be this part, and the increase will be this part. So let's say we're given a function and we're supposed to find the derivative or sketch the derivative. We notice that the function has a very positive slope, a very high positive slope. So our derivative will start at the very top. And then our derivative should hit a 0 at x equals 0. So let's go ahead and also draw the x and y axis. So at 0, our derivative is 0. So I'm gonna go ahead and make a point right there. And then at that was way too far away. Let's say we start like right here. And then we have a decrease of the function from 0 to 2. So those are negative slopes. The negative slope is probably at its highest right here, then it starts going back to 0. So it goes all the way up to like 1. So let's say at 1 we reach all the way up to 1. And then we hit 0 again right here. So at 2 we hit a 0 again. Every time you have a little every time you have one of these bad boys, it means that your derivative equals 0. And then over here, that's where your derivative was at its highest between 0 and 2, which happens to be, I'm saying it's negative 1. I would say it's negative 1. And I don't know why I went up there. It's supposed to be negative 1, not positive 1. So that's right here. Actually, looking at it again, might be negative 2. Actually looks more like negative 2. Don't rely on what I say, you know? It's between 1 and negative 2, but negative 1 and negative 2. So up here you can tell that it's going all the way back up to, well, it's going to 0 right here, which is why I made that point. And then it's going back to infinity around these areas. So I'm going to go ahead and make another point right there. And this will be your derivative function. There's a fly that's just bothering me. I hate flies. Alrighty, so that's kind of what I expected. This looks like a polynomial with a degree 3. You can tell because if I was to lower the function, this function would hit the x-axis 3 times, and this looks like a degree 2. Now I can't verify that that's a degree 3 because you don't know what's happening outside this little range, but I'm not surprised. That's all I'm saying. Let's continue. Oh, I'm still recording. Here's another example of drawing a derivative based on the sketch. We have a parabola. The parabola has a 0 or a maximum up here, so that's where I expect the derivative to be 0. So that's why this point was made. And then we have a negative slope, a positive slope up here around these areas. So our derivative is positive, And then after that, we're going to start having negative slopes. So our derivative is negative. And here are intervals of increase. We have an increase from negative infinity to negative 3, and a decrease from negative 3 to infinity. Please make sure you don't include infinity or negative 3 in your sets. What I mean by that is use parentheses. If you were using brackets, that would include the endpoints, but we don't want to do that. So let's continue. Find intervals of increase and decrease, then draw the function to the derivative. Same thing. You identify the points at which you have minimums and maximums. Let's go ahead and use gray. I didn't know I have gray as an option. Let's go ahead and mark them real quick. Boom, 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 boom. And over here, when you have an arrow like this, it means that we are approaching infinity. So, excuse me on that. Let's have all the decreasing first. Let's do all the decreasing derivatives. So decreasing and then increasing. Alrighty. When we look at the function, we have where do we have the negative slopes? The negative slopes are happening right here. So from negative infinity, all the way to this point, which I'm guessing is negative 3. Do we have any other decreasing negative slopes? We sure do. From negative 1 to, man, this is such a hard thing to read. That's too much writing. I'm guessing that's 1. And then, where else do we have negative? That's it. And then increasing, we have negative 3 to negative 1. And then from 1 to infinity. I want to make sure I didn't mess up, so am I counting for all the places of the graph? Negative infinity to negative 3, negative 3 to negative 1, negative 1 to 1, 1 to infinity. Okay, that's good. So that's how you get all the intervals, and drawing the graph is also just the same way. You know, you start off with a very negative slope, I'm assuming, so you want to start off down here, and then you want to increase until you hit that point at which you're supposed to start decreasing, which happens at negative 3. So at negative 3, you want to hit the x-axis, and then actually maybe draw the x-axis points first. Whenever this has a maximum minimum, just make a little dot at the x-axis. Boom. Very good. So we're going down. We're going up, and then we're going to hit that x-axis. Are we going to go through, or are we going to go down? Well, we are changing from a decrease to an increase, which means that we must be in the positive region. So we'd have to go to the point. And then at 1, we are again going from a increase to a decrease, so we must go below the x-axis. And then at 1, sorry, previously negative 1, but now we're at 1, we are going from a decrease to an increase. So we must go above the x-axis. So that's pretty much how you draw it. And these are just estimations. You don't have to be perfect. Here's another example. We have the function negative x cubed minus 3x squared plus 1. We're supposed to find the derivative using the power rule. You can find it right here. And then this is computer graphed. Just do the same thing. Find out where these points are. And then at those points, create these little, let me use green, create these x-intercepts. And then just look at where we have positive and negative slopes. Since we have, is that a positive or negative slope? It's negative, so we're going to be below the x-axis. Is this a positive or negative slope? It's positive, so we're going to be above the x-axis. Is this a positive or negative slope? That's a negative. So the derivative, since it represents a slope, must be below the x-axis. Anything above the x-axis implies it's positive. Anything below the x-axis implies it's negative. Let's move on. Ooh, I like this. For what values of x is the derivative positive? What is the graph of f of x during these values? Misread that one. What is the graph of f of x doing in these values. Okay, oh, what's happening, gotcha. Alrighty, I've created my infamous x-axis. That's only funny to me. Alright, so when I take the derivative and I then factor it to find out where the zeros are for the derivative, I find that it's -2 because of this one, and then 0 because of this one. So these are points of interest. To the left of -2, we would have a negative here. So let me just use a different color. We would have a negative here, and then we would have a negative here, negative times to the left of -2. Yeah, that would be negative, and that would be a positive. Oh, I'm sorry. That would be a positive, and then that would be negative, which would make this negative. And then between -2 and 0, we would have a negative here and a negative, so that would be positive. And then after 0, we would have a negative and a positive, making it a negative. So for what values is the derivative positive? It would be -2, 0. So for the other question, what is the graph of f of x doing in these values? By definition, whenever a derivative is positive, it's increasing since the derivative is a change of rate. For the next part, for what values of x is f of x decreasing? That would be whenever the derivative is negative. And when is the derivative negative? That's from -infinity to -2 and from 0 to infinity.